Welcome to Educator.com. Today we're going to work on solving systems of equations by the substitution method. Previously, we learned how to solve a system of equations using graphing. However, graphing is not always that practical, and it can be hard to get an exact answer. So there are other methods to use to solve systems of equations. So this first one, substitution. A system of equations can be solved by substituting an expression for one of the variables obtained from one of the equations into the other equation. The result will be one equation with one variable. And from there you can solve it. For example, if I have two equations such as 4x plus 5y equals 10. So let's say I have a system of equations. This is the first, and the second is that x equals 2y plus 3. I have a situation where I have x written in terms of y. So what I can do is simply substitute in this expression for x in the other equation, in the first equation. Now what I have is one equation with one unknown, and I'm just going to go through and use techniques we've discussed before, the distributive property, the addition principle, multiplication principle, to isolate y. Once I have a value for y, then it's just a matter of inserting that y value into either of my equations to find x. Now, this was a great situation because x was already written out here in terms of y, but it's not always that simple. Sometimes you have to isolate one of the variables, either x or y. You have to isolate a variable from the equation and then substitute. Now, a great situation to use substitution is when you see a situation where you have a variable with a coefficient of 1. If I look at a system of equations and I see, okay, I've got an x or a y with a coefficient of 1, that means I can very easily write it out in this form, x equals, and then in terms of y, or with y equals, and then have my x value on the other side of the equation. So be looking out for situations where you have one variable with a coefficient of 1, and then realize that that's a great time to use the substitution method. Because as we learn more methods of solving systems of equations, one thing that you'll need to do is select the easiest method to use. Number of solutions. If the system of equations produces a result of the form c equals c for some constant c, the system has an infinite number of solutions. So a system of equations can have an infinite number of solutions. So if I'm going through, I substitute, and then I find that at the end of solving that out, I end up with a constant such as 6 equals 6, then I would have an infinite number of solutions. Remember when we talked about solving systems of equations by graphing? In that method, you sometimes saw that when you went and plotted out two lines, you went and graphed those out, you found that they were actually the same line. So you had two equations, you went, graphed one out, you went and graphed the second out, and you found they were the same line. And when those equations turned out to describe the same line, what we said is that we have an infinite number of solutions, that every single point on that line is a set of solutions for this equation. And this is the same thing, except when you're using substitution, you're not doing it visually, you're not graphing, you're not seeing what the lines look like. However, mathematically, you can see that they're the same when it comes out to a constant equaling a constant. Another situation that can occur is if the result is c equals d for two different constants, c and d, then the system has no solutions. So if I end up with this, then there's no solutions. Because c, in fact, does not equal d. For example, if it said 5 equals 7 or -2 equals 15, these are not true, so there are no solutions. This is analogous to the situation of parallel lines. Recall with the graphing method, sometimes you go and you graph out two equations and you realize, okay, they have the same slope, they are parallel lines. They're parallel lines, they're never going to intersect, there's no solution. So again, we have several different possibilities. We can have one solution, which would be the point of intersection of two lines if you did it graphically. We could have an infinite number of solutions, and what we'll see mathematically is that a constant equals a constant. Or we can come out with a constant and then it says equals another constant, which does not hold up. So we say that we have no solutions. In our first example, we're asked to solve this system of equations. And as soon as I look at this, I think this is a great setup for me to use substitution, because I have a variable with a coefficient of 1. So this is a good situation to use substitution. Again, it's not the only time you can use substitution, because you can isolate a variable and get an equation in this form. But this is just the perfect situation, the easiest situation. So what I'm going to do is I'm going to take my second equation and I'm going to substitute this expression in for the x value. And what that will give me is one equation with one unknown. So that's going to be 2 times 3y minus 4 plus 5y equals 17. Using the distributive property to multiply this out, I get 6y minus 8 plus 5y equals 17. I'm going to combine like terms. So I have 11y minus 8 equals 17. Next, I'm going to add 8 to both sides in order to isolate the y, because what I'm trying to do is solve for y. My negative 8 and 8, those two cancel out on the left, and on the right I end up with 17 plus 8, which is 25. Dividing both sides by 11, I end up with y equals 25 over 11. Once I've got a value for y, it's very easy for me to find the value for x. Using either equation, you can use either equation and insert this value 25 over 11 for y and then solve for x. I'm going to use this first equation because it's already set up really well for me to solve for x. So I know that y equals 25 over 11. So I'm going to simply insert that value here. And I'm going to find that x equals 75 over 11 minus 4. In order to go farther with this, I have to find a common denominator. And so I'm going to use 11 as my common denominator. And to do that, I'll have to make this 44 over 11. Simply subtract, and I'm going to find that x is 31 over 44. So my solution for this set of equations is that x equals 31 over 44 and y equals 25 over 11. We started out with a situation where we already had a variable that was isolated, x equals 3y minus 4. Then I took that expression and substituted it for x in the other equation. And that gave me 2 times 3y minus 4 plus 5y equals 17. At this point, I simply had one equation with one variable, with one unknown. And then I used our usual techniques, such as the distributive property, addition principle, multiplication and division principles, to solve for y. Once I found that y is 25 over 11, all I had to do is substitute for y in either equation. So I took the first equation, substituted my y value of 25 over 11, and solved that out to find that x is 31 over 44. So this was an example of using substitution to solve a system of equations. Again, we're asked to solve the system of equations. And I'm looking at this, and I don't have a variable with a coefficient of 1, but pretty close. This is a coefficient of -1. So that's not going to be very difficult for me to get the y isolated. What I need to do is express one of the variables in terms of the other, and it can be x or y. So I'm going to start out with 3x minus y equals 7. I'm going to subtract both sides by 3x, and I'm going to have minus y equals -3x plus 7. Then I'm going to simply multiply by -1, so that I'll have y equals 3x minus 7. Now I'm at the point I started from in the last example, where I have one variable expressed in terms of the other. So I used this equation for my variable to find a variable in terms of the other, and I'm going to plug this expression into the second equation. So my second equation is 4x minus 6y equals 18. And I'm going to rewrite that substituting 3x minus 7 for y. Then I go ahead and do the math, and I get 4x minus 18x plus 42. -6 times -7 will give me a positive 42 equals 18. Simplify this by combining like terms. I have 4x minus 18x. That simplifies to -14x plus 42 equals 18. Now I'm just working on isolating the x. I need to move the number 42 to the other side, and I'll do that by subtracting 42 from both sides. My 42's cancel out. 18 minus 42 is -24. Finally, I'm going to divide both sides by -14. And what this is going to give me is that x equals 24 over 14. And you could further simplify that to x equals 12 over 7. Okay, now that I got down to here and I have a value for x equals 12 over 7, I can go back to either equation, substitute that value in for x, and solve for y. And instead of going to the original equation, another possibility is to go to a form of the original equation. And remember that I just manipulated that first equation into the form y equals 3x minus 7. And I'm going to use this to plug my x value in because I already have y isolated. Remember, what I'm doing now is looking for y. So it makes sense for me to use an equation where I already am solving for y. I already have solved for y. So I'm going to say that y equals 3x minus 7. And I'm going to go ahead and substitute in this x value that I found, which is 12 over 7 minus 7. Continue simplifying. So this is 36 over 7 minus 7. I need a common denominator to go any farther. So I'm going to convert 7 to 49 sevenths. And I'm going to find that y equals 13 sevenths. So my solution to this system of equations is that x equals 12 over 7 and y equals 13 over 7, 13 sevenths. When I started out up here, I saw that I had to isolate y and also make it positive in order to work with it easily for the substitution method. So my first step was just to get this equation in the form y equals 3x minus 7. From there, I plugged this expression into my second equation, 4x minus 6y equals 18. By substituting 3x minus 7 for y, I ended up with one equation with one unknown. From there, it was a matter of solving for x. Once I got that x equals 12/7, I went back to this form of the equation because it already had y isolated and put in 12/7 in lieu of x. Result was y equals 13/7. For this third example, we're going to be solving the system of equations 4x minus 6y equals 12 and 3x plus 9y equals 15. I'm looking at this and I don't have a variable with a coefficient of 1 or even -1, so I'm going to have to work on isolating an x or y. And I'm going to select the second equation, 3x plus 9y equals 15, and I'm going to isolate the x. So I'm going to rewrite this as 3x equals -9y plus 15. And then all I have to do is divide both sides by 3 to get that x equals -3y plus 5. So I now put this second equation into a different form where I have x isolated. Once I've done that, I go about with my usual steps for the substitution method. The first equation is 4x minus 6y equals 12. And I'm always going to substitute the expression into the other equation, not back into itself. So I have this expression -3y plus 5, and I'm going to substitute that for x in the other equation. And that's going to give me 4 times -3y plus 5 minus 6y equals 12. Okay? So simply substituting this expression for x. Using the distributive property, that's going to give me -12y, and then multiply those two out, plus 20 minus 6y equals 12. Simplify by combining like terms. -12y and -6y combine to equal -18y. Now I need to move that 20 to the right side of the equation, which is going to give me -18y, 20's cancel out, equals -8. Divide both sides by -18. And I'm going to end up with y equals 8 over 18, which simplifies to 4/9. So I've solved for y, and once I've solved for y, I can go back and solve for x. Again, I'm not going to go back to either of these two to solve for x. I could, but it's more complicated. I've already got this second equation in a form that would be really easy for me to solve for x. So I'm going to go back to this equation, x equals -3y plus 5, and I'm going to take my y value and substitute it in. So I have x equals -3 times 4/9 plus 5. Or x equals -12/9 plus 5. I can simplify this out to x equals -4/3 plus 5. And then I'm going to have to find a common denominator, which is going to be 3. So that's going to be -4/3 plus 15/3. Therefore, x is going to equal 11/3. My solution is that x equals 11/3 and y equals 4/9. When I started with that original equation, it was harder to do substitution because I first had to manipulate one of the equations so that I had a variable isolated. I solved for x in the second equation. Once I had that, I simply inserted this expression for x in that first equation, in my other equation, and solved for y. Once I've solved for y, I went back to my simple equation here and substituted 4/9 for y, followed through on the math, and found that x equals 11/3. Next, solve the system of equations 2x minus 4y equals 10 and -6x plus 12y equals -30. Again, I don't have the ideal situation. I don't have x or y in any equation with a coefficient of 1, but I can get it that way. And I'm going to work with this first equation, and I'm going to solve for x. 2x minus 4y equals 10. So my goal is to isolate x. Therefore, I'm going to move the 4y to the other side, and I'm going to divide both sides of the equation by 2. And that's going to give me x equals 2y plus 5. So what I did is I took that first equation and I moved things around. I manipulated it algebraically, mathematically, to get x equals 2y plus 5. Remember, I'm going to insert that expression for x into the x where in place of x in the other equation. Okay. So I look at that second equation, negative 6x plus 12y equals negative 30. All right, as usual, I substitute in 2y plus 5 right here instead of x. Multiply this out. That will give me negative 12y minus 30 plus 12y equals negative 30. Now I go to simplify this, and what I notice is that the y's drop out. I have negative 12y plus 12y on the left side of the equation. So when those drop out, what I'm left with is a constant equals a constant. Recall, we talked about the situation where you can end up with c equals c. And when it does, that gives you an infinite number of solutions. If you graphed out these two equations, you would find that they are the same line. And any point along that line is a solution for this set of equations. Therefore, there's an infinite number of solutions. Remember, if we ended up with a situation where we had a constant, where we had, say negative 30 equals 12, that would have been a constant equaling a different constant. That would have been no solution. And that's not the situation here. Here we actually have a true statement, a true equation, negative 30 equals negative 30. So I have an infinite number of solutions for this set of equations, for this system of equations. So today on educator.com, we learned how to solve systems of equations using the substitution method. Next time, we're going to learn more methods for solving systems of equations.